صباح الخير طلابي الأعزاء. في المحاضرة الماضية نحن بلشنا في الكربوهيدرات، حكينا عنهم as a fuel of energy، حكينا قديش هذه الكربوهيدرات مهمة inside your body، حكينا عن عملية التسمية كيف احنا بنسمي وكيف بنعمل classification للكربوهيدرات. في محاضرة اليوم رح نستكمل جزء الشكل الكيميائي للكربوهيدرات، وبنهاية المحاضرة إن شاء الله رح نرجع نحكي عن كيف بصير عملية الديجريديشن والابزوربشن للكربوهيدرات inside your body. فبمحاضرة اليوم رح يكون شوي الوضع مختلف، رح نحكي chemical structure على غير العادة، رح نركز كتير على الكيميكال structure. حناخد فيديو من اليوتيوب، هذا الفيديو رح يكون فيه شرح كيف الكيميكال ستراكشر للكربوهيدرات وكيف السايكلايزيشن اوف الكربوهيدرات عم بيصير، وبعدين رح نكمل شرح اللي هو كيف جسمنا بيتعامل مع الكربوهيدرات، بمعنى كيف جسمك انت بيعمل degradation او break down للكربوهيدرات وكيف بعدين بيصير لها absorption.
Structure of monosaccharides in the last video, we can now consider how monosaccharides cyclize to form rings. In cells, pentoses and hexoses are predominantly found in cyclic rather than linear forms. Let's use glucose as an example. Cyclic structures form when a hydroxyl group, usually the one on the highest numbered chiral carbon, performs a nucleophilic attack on the carbon of the carbonyl group. The hydroxyl loses a proton to the aqueous environment, while the oxygen of the carbonyl picks up a proton to form an OH group. The result is a new carbon-oxygen bond and a structure with a six-membered ring, 5 carbons and 1 oxygen. This reaction is reversible, but the cyclic or ring form is favored. The resulting ring structure is awkward to represent as a Fischer projection, so W. Norman Hayworth developed the Hayworth projection for cyclic monosaccharide structures. The ring structure is represented as a flat six-sided shape, viewed in perspective, with the lower horizontal bond close to you and the upper horizontal bond further away. The chemical groups at each carbon are shown as either above the plane of the ring or below the plane of the ring. To help you see which carbon is which, let's add numbers to the structures. Look at carbons 2, 3, and 4. Notice that the OH groups that were on the right side of the Fischer projection are on the lower side of the Hayworth projection. And the OH group that was on the left side of the Fischer projection is on the upper side of the Hayworth projection. As I mentioned earlier, the doubly bonded oxygen on carbon 1 is converted to a hydroxyl group upon cyclization. As a result, carbon 1 becomes a chiral carbon in the ring structure. You can see that it is bonded to 4 different chemical groups. I have shown the hydroxyl group on carbon 1 in the down position of this Hayworth projection, but in fact the hydroxyl could also be in the up position. Which position it ends up in depends on the angle at which the hydroxyl of carbon 5 attacks the carbonyl during the cyclization reaction. This means that there are 2 possible ring structures for D-glucose, shown here. They differ only in the position of the hydroxyl group on the carbon that used to be doubly bonded to oxygen. This carbon is called the anomeric carbon, and these structures are said to be anomers of each other. The structure in which the hydroxyl on the anomeric carbon is on the opposite side of the ring structure from the highest numbered carbon is called the alpha structure. So, in the structure on the left, the hydroxyl on the anomeric carbon points down on the bottom of the ring, while carbon 6 points up on the top of the ring. The structure on the left is therefore alpha glucose. In the structure on the right, the hydroxyl on the anomeric carbon is on the same side of the ring as the highest numbered carbon, and so the structure on the right is beta glucose. An easy way to remember the naming convention is that alpha and opposite both start with vowels, while beta and same both start with consonants. Remember that the cyclization reaction is reversible. This means that the anomers of a monosaccharide can convert back and forth in solution. The ring structure can open to form the linear structure and then reclose with the hydroxyl in either the alpha or the beta configuration. When monosaccharides form a six-membered ring, they are called pyranoses. This is because pyran is a molecule consisting of a six-membered ring of 5 carbons and 1 oxygen, just like a monosaccharide six-membered ring. Thus, when glucose is in its six-membered ring form, it could be called glucopyranose. More specifically, the molecule shown here is alpha-D-glucopyranose because the anomeric hydroxyl is in the alpha position and the highest numbered chiral carbon is in the D configuration. Remember that in this course all sugars shown will be in the D forms. 5-membered monosaccharide rings, such as ribose, resemble the molecule furan and are called furanoses. So, in its cyclic structure, ribose could be referred to as alpha-D-ribofuranose. It's important to remember that a Haworth projection is a simplified depiction of a monosaccharide. In reality, it is energetically unfavorable for all of the atoms of the ring to exist on the same plane. Six-membered rings are found in either chair or boat conformations, as shown. To help you compare structures, we can label the numbers of the carbons in the ring. The chair conformation is more energetically favorable than the boat conformation. 5-membered rings can form C2 endo or C3 endo conformations,